Have you ever used something like ChatGPT and just been completely blown away, or maybe even a little bit creeped out by how smart it seems? Well, you are in exactly the right place. Today, we're going to pull back the curtain and demystify how these large language models actually work. We'll go from the really simple math at their core all the way up to the huge, complicated questions they're posing for all of us. Let's jump in. So here's our game plan. First, we're going to start with the core idea behind all of this, which is, you'll be surprised to hear, basically a prediction game. Then we'll look at how we got from that simple game to the absolute behemoths we have today. After that, we'll get practical and talk about the art of conversation, how to actually talk to these things. Then we'll put on our lab coats and figure out how we measure an LLM's mind. And finally, we'll have to confront the ghost in the machine, the big, thorny problems, and the incredible potential. All right, let's start at the beginning. Section 1, the core idea. It really all boils down to a prediction game. While the results feel like pure magic, the engine driving it is surprisingly simple. So when you see an AI write a totally coherent essay or spit out a piece of code that actually works, what is really going on in there? I mean, it sure looks like it's thinking, right? But the process underneath is something else entirely. It's both ways simpler and somehow way more complex than you'd imagine. Believe it or not, the entire multi-billion-dollar field of large language models is built on a feature you use every single day without even thinking about it: your phone's autocomplete. That's it. The fundamental task, the prime directive of a language model, is just to guess the next word in a sequence. And here's what that looks like in the language of math. At its absolute heart, an LLM is a probability machine. It's just trying to solve this one equation over and over again. It's calculating the probability of the next word, that's what P of X sub T means, given all the words that came before it. That vertical line just means given. So if you type, "the cat sat on the model is running the numbers for every word it knows, mat, roof, planet, and it picks the one with the highest probability. That's the whole game. Everything else, all the complexity, is just about getting better and better at making that one single prediction. Okay, so if it's just a prediction game, how did we get from a simple autocomplete to a model that can write a sonnet about a toaster? Well, it wasn't a single aha moment. It was a whole series of really clever technological leaps over many decades. The very first attempts at this were pretty basic. They used a statistical method called n-grams. The idea is dead simple. You just take a massive pile of books and you count. You count up how many times you see sequences of words. So if in all your books the phrase "the cat sat on the" appears a million times and 90% of the time it's followed by Matt, well, Matt gets a really high probability score. It's just counting. But this simple counting method had a huge fatal flaw. It's called the sparsity problem. Just imagine a phrase that's perfectly logical but has never ever been written down before. Something like, "the purple flamingo ate a..." Because the n-gram model has never seen that exact sequence, the probability of any word coming next is zero. It just gets stuck. It has no way to be creative or generate a new sentence. All it can do is regurgitate sequences it's already seen. And this was the game changer. Researchers like the pioneering Yoshua Bengio suggested using neural networks instead. Now, instead of just counting rigid phrases, these models could actually learn the relationships between words. They represent words as points in a sort of conceptual space. So the model could learn that king is to queen as man is to woman. It could understand that cat and dog are kind of similar. This ability to generalize was the key that unlocked the door to understanding sentences they'd never seen before. Okay, so now we have these incredibly powerful neural models. The question is, how do we actually use them? How do we talk to them to get what we want? Well, that has become a whole new skill. You might even call it an art form. And that art is called prompt engineering. It's literally the practice of designing the perfect input to guide the model toward the output you're picturing in your head. And what's really key here is that you're not reprogramming the model itself. You're just getting better at asking the right questions. The simplest way to do this is called zero-shot prompting. You just give it a direct order, plain and simple. Classify this movie review as positive or negative. But you can get much better results with few-shot prompting. Here, you give it a few examples first. You show it the pattern you want. It's like you're teaching it on the fly without having to be a programmer. Now this is where things get really wild. For problems that need actual reasoning, a standard prompt can often lead the AI to jump to a quick conclusion and get it wrong. Just look at the example on the left. But if you use what's called chain of thought prompting, you're telling the model, hey, don't just give me the answer, show your work. And by forcing it to break the problem down step by step, it actually reasons its way to the correct answer. It's a night and day difference. And this isn't just some random trick someone found. This was a landmark discovery. A paper from Google researchers in 2022 showed that this super simple prompting technique could basically unlock emergent reasoning abilities in these models, abilities no one had explicitly programmed into them. It was like they found a hidden feature. And here's the craziest part. They found that sometimes all it took was adding a simple, almost magical phrase to the end of a prompt. Let's think step by step. Just adding those words could trigger this whole different, more accurate mode of processing. It's an absolutely fascinating look into the black box of how these things think. So we've got these models that can follow instructions and even seem to reason, but how do we know if they're actually any good? How do we measure them scientifically and say, yep, Model A is definitely smarter than Model B? How do we give them their final exam? Let's do a quick thought experiment. Imagine two models. You give both the phrase, the cat is on the. Model 1 thinks the most likely next words are protein and physics. Yikes. Model 2 thinks the most likely words are roof and tree. I mean, it's pretty obvious which one has a better grasp on how the world works, right? But we need a formal way to capture that intuition with a number. And that number is called perplexity. It's a fancy word, but the concept is really simple. You can think of it as a measure of how surprised the model is when it reads a real sentence. A good model that actually understands language won't be very surprised by normal human text. A bad model will be constantly surprised. So in this case, a lower perplexity score is better. It means the model is less confused by reality. So the entire goal when you're training one of these models is to just minimize that surprise factor. You want to get the perplexity score as low as you possibly can. Mathematically, that's the exact same thing as maximizing the probability the model assigns to real, sensible sentences. And, this is critical, we always test them on data they've never seen before to make sure they're actually learning and not just memorizing the textbook. No cheating allowed. Okay, and for our final section, we have to talk about the ghost in the machine. Because for all their incredible power, these models come with some really serious, really complex challenges that we are just starting to get our heads around. One of the sharpest critiques out there frames these AIs as stochastic parrots. It's a term from researchers like Emily Bender, and it poses a really fundamental question. Is the model actually understanding what it's saying, or is it just an incredibly advanced parrot, one that can stitch together words and sentences it's heard in a statistically plausible way, but with zero actual comprehension of the meaning behind them? And that whole understanding versus mimicking debate leads to some very real-world problems. We've got hallucinations, where the models just make stuff up that sounds completely plausible but is totally false. There are huge intellectual property battles over training these things on the entire internet. The environmental cost is staggering. These data centers use millions of gallons of water for cooling. And there's even this weird psychological problem of sycophancy, where the models learn to just tell users what they think they want to hear, reinforcing their biases. You know, to really put this moment in context, just look at this timeline. The whole field of AI was born back in 1956. We had these big moments for sure, but the progress was often slow and steady. And then, look what happens starting around 2012. The pace just goes vertical. From AlexNet to BERT to ChatGPT putting this power in everyone's hands, we are living in a moment of absolutely mind-bending acceleration. In the end, maybe the best way to think about these models is as a kind of mirror. They're trained on this vast, sprawling ocean of human text. Our books, our websites, our arguments, our poems, our code, our hopes, and our fears. They are quite literally a reflection of us. So the biggest question we face isn't really a technical one. It's a human one. What version of ourselves, our knowledge, our biases, our virtues, do we actually want this mirror to reflect back at us?